Data compression. Suppose on my computer is a picture of a selfie, the same selfie we looked at in the previous video, that has a total of 100 pixels. Since each pixel is 24 bits in length due to the RGB values each being 8 bits long, the total amount of storage that this picture would require is 2400 bits. The goal for data compression is to store only a percentage of that data in memory, not the entire 2400 bits. The reason for that is, since we're not looking at this picture or any other picture for that matter 24/7, why have 100% of the data stored in our computer 24/7? Rather, the goal of data compression is to store only a percentage of that data in memory and only bring out the entire full data when we're looking at the picture. Now, we don't want to compress the data too much to the point where we're no longer able to decompress it back to its original state. We still want to be able to decompress to its original state, so we only compress it as much as we can to the point where there's still enough information left to decompress it back to its original state. Now, this is a big deal when working with very large files, like a movie file, for example. Consider these 3 movie files in front of you that combine to take up 16 megabytes of memory. Now, it's possible your computer or laptop may not have enough storage to fit all 3 of these files in your computer. However, if we were to compress these files by 90%, for example, then it would be possible. What data compression would do is it would store the compressed version of these 3 files in memory, not the full version, but the compressed version, then decompress the file you want to use and only the file you want to use only when you want to use it, only when you want to watch that movie. Then when you're finished watching that movie, it'll then recompress it back into its smaller state and put it back in storage. Now we'll look at an example of data compression with a text file. Suppose my text file contained the following characters. As you can see, each character in this paragraph is repeated at least once. So here's how we could compress this file. Right? Rather than write 4 H's, we could write the letter H followed by a 4, indicating that there are 4 H's. Then instead of writing 3 E's, we could write the letter E followed by a 3. Then instead of 2 L's, we'll write the letter L followed by a 2. Instead of 3 O's, we'd write the letter O followed by a 3. Then instead of 4 W's, we'll write a W instead of 4. Instead of 1 O, we'll write O and 1. Instead of 3 R's, the letter R and 3. Instead of 2 L's, the letter L and 2. Instead of 4 D's, the letter D and the number 5. And instead of 6 exclamation points, we'll write the exclamation point followed by the number 6. And then repeat this process on the remainder of the paragraph. This kind of data compression is called run length encoding. The original text file had 139 characters, which uses up approximately 1.1 kilobytes of memory. The decompressed version had only 91 characters, which uses approximately 0.7 kilobytes of memory. So by compressing the data, we're able to save almost half a kilobyte of memory. Not only that, but we compressed it in a way such that we'll be able to decompress the data back to its original version by simply looking at the letter and the number that follows it. Now, obviously, this particular compression algorithm wouldn't be useful for most text because most text don't repeat letters in this fashion. However, it's still a good algorithm to study and discuss because it's a good example of what the general goal of data compression is, which is to reduce the amount of information stored to save space, but still leave enough information that you're able to decompress that data back to its original state when needed.